There are publicly available fine-tuned LoRa adapters that you can use the way you'd use pre-trained models. You can find them on Hugging Face 26 or Inetia TIVs like Adapter Hub. You might be wondering, LoRa sounds great, but what's the catch? The main drawback of LoRa is that it doesn't offer performance as strong as full fine-tuning. It's also more challenging to do than full fine-tuning as it involves modifying the model's implementation, which requires an understanding of the model's architecture and coding skills. However, this is usually only an issue for less popular base models. PEFT frameworks, such as Hugging Face's PEFT, Axolotl, Unsloth, and LitGPT, likely support LoRa for popular base models right out of the box. Quantized LoRa. The rapid rise of LoRa has led to the development of numerous LoRa variations. Some aim to reduce the number of trainable parameters even further. However, as illustrated in Table 7.6, the memory of a LoRa adapter is minimal compared to the memory of the model's weights. Reducing the number of LoRa parameters decreases the overall memory footprint by only a small percentage. Table 7.6. The memory needed by LoRa weights compared to that needed by the model's weights. Model's weights memory, 16 bits, LoRa trainable params, R equals 2, query and key matrices, LoRa adapter memory, 16 bits, Llama 2, 13B, 26 GB 3. 28 M6. 55 MB GPT-3, 175B, 350 GB 18. 87 M37. 7 MB fine-tuning techniques, 345. 27 kilo-RA isn't the only quantized LoRa work. Many research labs have been working on quantized LoRa without publicly discussing it. Rather than trying to reduce LoRa's number of parameters, you can reduce the memory usage more effectively by quantizing the model's weights, activations, and/or gradients during fine-tuning. An early promising quantized version of LoRa is kilo-RA, Detmers et al., 2023. 27 in the original LoRa paper, during fine-tuning, the model's weights are stored using 16 bits. Kilo-RA stores the model's weights in 4 bits but dequantizes, converts, them back into BF16 when computing the forward and backward pass. The 4-bit format that kilo-RA uses is NF4, normal float 4, which quantizes values based on the insight that pre-trained weights usually follow a normal distribution with a median of 0. On top of 4-bit quantization, kilo-RA also uses paged optimize errors to automatically transfer data between the CPU and GPU when the GPU runs out of memory, especially with long sequence lengths. These techniques allow a 65B parameter model to be fine-tuned on a single 48 GB GPU. The authors fine-tuned a variety of models, including Llama 7B to 65B, in the 4-bit mode. The resulting family of models, called Guanaco, showed competitive performance on both public benchmarks and comparative evaluation. Table 7.7 shows the ELO ratings of Guanaco models, GPT-4, and ChatGPT in May 2023, as judged by GPT-4. While Guanaco 65B didn't outperform GPT-4, it was often preferred to ChatGPT. Table 7.7. ELO ratings of Guanaco models compared to popular models in May 2023 using GPT-4 as a judge. The experiment is from kilo-RA, Detmers et al., 2023. Model size ELO GPT-4, 1348 plus or minus 1 Guanaco 65B 41 GB 1022 plus or minus 1 Guanaco 33B 21 GB 992 plus or minus 1 Vicuna 13B 26 GB 974 plus or minus 1 ChatGPT 966 plus or minus 1 Guanaco 13B 10 GB 916 plus or minus 1 Bard 902 plus or minus 1 Guanaco 7B 6 GB 879 plus or minus 1. The main limitation of kilo-RA is that NF4 quantization is expensive. While kilo-RA can reduce the memory footprint, it might increase training time due to the extra time required by quantization and dequantization steps. 346, Chapter 7, Fine-Tuning. Due to its memory-saving promise, quantized LoRa is an active area of research. Other than kilo-RA, Quantized LoRa works include QLORA, Su et al., 2023, ModelORA, Yin et al., 2023, and IRQLORA, Chin et al., 2024. Model merging and multitask fine-tuning. If fine-tuning allows you to create a custom model by altering a single model, model merging allows you to create a custom model by combining multiple models. Model merging offers you greater flexibility than fine-tuning alone. You can take two available models and merge them together to create a new, hopefully more useful, model. You can also fine-tune any or all of the constituent models before merging them together. While you don't have to further fine-tune the merged model, its performance can often be improved by fine-tuning. Without fine-tuning, model merging can be done without GPUs, making merging particularly attractive to indie model developers that don't have access to a lot of compute. The goal of model merging is to create a single model that provides more value than using all the constituent models separately. The added value can come from improved performance. For example, if you have two models that are good at different things on the same task, you can merge them into a single model that is better than both of them on that task. Imagine one model that can answer the first 60% of the questions and another model that can answer the last 60% of the questions. Combined, perhaps they can answer 80% of the questions. The added value can also come from a reduced memory footprint, which leads to reduced costs. For example, if you have two models that can do different tasks, they can be merged into one model that can do both tasks but with fewer parameters. This is particularly attractive for adapter-based models. Given two models that were fine-tuned on top of the same base model, you can combine their adapters into a single adapter. One important use case of model merging is multitask fine-tuning. Without model merging, if you want to fine-tune a model for multiple tasks, you generally have to follow one of these approaches. Simultaneous fine-tuning. You create a dataset with examples for all the tasks and fine-tune the model on this dataset to make the model learn all the tasks simultaneously. However, because it's generally harder to learn multiple skills at the same time, this approach typically requires more data and more training. Fine-tuning techniques. 347. 28. My book, Designing Machine Learning Systems, has a section on ML on the cloud and on the edge. Sequential fine-tuning. You can fine-tune the model on each task separately but sequentially. After train a model on task A, train it on task B, and so on. The assumption is that it's easier for models to learn one task at a time. Unfortunately, neural networks are prone to catastrophic forgetting. Kirkpatrick et al., 2016. A model can forget how to do an old task when it's trained on a new task, leading to a significant performance drop on earlier tasks. Model merging offers another method for multitask fine-tuning. You can fine-tune the model on different tasks separately but in parallel. Once done, these different models are merged together. Fine-tuning on each task separately allows the model to learn that task better. Because there's no sequential learning, there's less risk of catastrophic forgetting. Model merging is also appealing when you have to deploy models to devices such as phones, laptops, cars, smartwatches, and warehouse robots. On-device deployment is often challenging because of limited on-device memory capacity. Instead of squeeze multiple models for different tasks onto a device, you can merge these models together into one model that can perform multiple tasks while requiring much less memory. On-device deployment is necessary for use cases where data can't leave the device, often due to privacy, or where there's limited or unreliable internet access. On-device deployment can also significantly reduce inference costs. The more compute time you can offload to user devices, the less you have to pay to data centers. 28. Model merging is one way to do federated learning. McMahon et al., 2016, in which multiple devices train the same model using separate data. For example, if you deploy Model X to multiple devices, each copy of X can continue learning separately from the on-device data. After a while, you have multiple copies of X, all trained on different data. You can merge these copies together into one new base model that contains the learning of all constituent models. The idea of combining models together to obtain better performance started with model ensemble methods. According to Wikipedia, ensembling combines multiple learning algorithms to obtain better predictive performance than could be obtained from any of the constituent learning algorithms alone. If model merging typically involves mixing parameters of constituent models together, ensembling typically combines only model outputs while keeping each constituent model intact. 348, Chapter 7, Fine-Tuning. 29. You can read more about ensemble methods in my book Designing Machine Learning Systems. For example, in ensembling, given a query, you might use 3 models to generate 3 different answers. Then, a final answer is generated based on these 3 answers, using a simple majority vote or another trainable ML module. 29. While ensembling can generally improve performance, it has a higher inference cost since it requires multiple inference calls per request. Figure 7.13 compares ensembling and model merging. Just like model ensembles used to dominate leaderboards, many models on top of the Hugging Face's Open LLM leaderboard are merged models. Figure 7.13. How ensembling and model merging work. Many model merging techniques are experimental and might become outdated as the community gains a better understanding of the underlying theory. For this REA Sun, I'll focus on the high-level merging approaches instead of any individual technique. Model merging approaches differ in how the constituent parameters are combined. 3 approaches covered here are summing, layer stacking, and concatenation. Figure 7.14 shows their high-level differences. Fine-tuning techniques, 349. Figure 7.14. 3 main approaches to model merging: summing, layer stacking, and concatenation. You can mix these approaches when merging models, e.g., summing some layers and stacking others. Let's explore each of these approaches. Summing. This approach involves adding the weight values of constituent models together. I'll discuss 2 summing methods, linear combination and spherical linear interpolation. If the parameters in 2 models are in different scales, e.g., one model's parameter values are much larger than the others, you can rescale the models before summing so that their parameter values are in the same range. Linear combination. Linear combination includes both an average and a weighted average. Given 2 models, A and B, their weighted average is, merge, A, B, equals WA plus WB WA plus WB. Figure 7.15 shows how to linearly combine 2 layers when WA equals WB equals 1. 350, Chapter 7, Fine-Tuning. 30. Averaging works not just with weights but also with embeddings. For example, given a sentence, you can use a word embedding algorithm to generate an embedding vector for each word in the sentence, then average all these word embeddings into a sentence embedding. When I started out in ML, I couldn't believe that averag ing seems to just work. It's magical when simple components, when used correctly, can create something so wonderfully perplexing, like AI. Figure 7.15. Merging parameters by averaging them. Linear combination works surprisingly well, given how simple it is. 30. The idea that multiple models can be linearly combined to create a better one was studied as early as the early 1990s, Peroni, 1993. Linear combination is often used in federated learning, Wang et al., 2020. You can linearly combine entire models or parts of models. Model soups, Wertzman et al., 2022, showed how averaging the entire weights of multiple fine-tuned models can improve accuracy without increasing inference time. However, it's more common to merge models by linearly combining specific components, such as their adapters. While you can linearly combine any set of models, linear combination is the most effective for models fine-tuned on top of the same base model. In this case, linear combination can be viewed through the concept of task vectors. The idea is that once you've fine-tuned a model for a specific task, subtracting the base model from it should give you a vector that captures the essence of the task. Task vectors are also called delta parameters. If you fine-tune using LoRa, you can construct the task vector from the LoRa weights. Task vectors allow us to do task arithmetic, Ilharco et al. 2022, such as adding 2 task vectors to combine task capabilities or subtracting a task vector to reduce specific capabilities. Task subtraction can be useful for removing undesirable model behaviors, such as invasive capabilities like facial recognition or biases obtained during pre-training. Linear combination is straightforward when the components to be merged are of the same architecture and of the same size. However, it can also work for models that don't share the same architecture or the same size. For example, if one model's layer fine-tuning techniques, 351, is larger than that of the other model, you can project one or both layers into the same dimension. Some people proposed aligning models before averaging to ensure that functionally related parameters are averaged together, such as in model fusion via optimal transport, Singh and Jaggi, 2020, Get Rebasin, merging models modulo permutation symmetries, Ainsworth et al., 2022, and merging by matching models in task parameter subspaces, Tam et al., 2023. While it makes sense to combine aligned parameters, aligning parameters can be challenging to do, and, therefore, this approach is less common on naive linear combinations. Spherical linear interpolation, SLIRP. Another common model summing method is SLIRP, which is based on the mathematical operator of the same name, spherical linear interpolation. Interpolation means estimating unknown values based on known values. In the case of model merging, the unknown value is the merged model, and the known values are the constituent models. Linear combination is one interpolation technique. SLIRP is another. Because the formula for SLIRP is mathy, and model merging tools typically implement it for you, I won't go into the details here. Intuitively, you can think of each component, vector, to be merged as a point on a sphere. To merge two vectors, you first draw the shortest path between these 2 points along the sphere surface. This is similar to drawing the shortest path between 2 cities along the Earth's surface. The merged vector of these 2 vectors is a point along their shortest path. Where exactly the point falls along the path depends on the interpolation factor, which you can set to be between 0 and 1. Factor values less than 0. 5 bring the merged vector closer to the first vector, which means that the first task vector will contribute more to the result. A factor of 0. 5 means that you pick a point exactly halfway. This middle point is the blue point in figure 7:16. SLIRP, as a mathematical operation, is defined with only 2 vectors, which means that you can merge only 2 vectors at a time. If you want to merge more than 2 vectors, you can potentially do SLIRP sequentially, i.e., merging A with B, and then merging that result with C. 352, Chapter 7, Fine-tuning. 31 The assumption is that the parameters that undergo the most substantial changes during fine-tuning are the ones most crucial for the target task. Figure 7:16. How SLIRP works for 2 vectors T1 and T2. The red line is their shortest path on the spherical surface. Depending on the interpolation, the merged vector can be any point along this path. The blue vector is the resulting merged vector when the interpolation factor is 0. 5. Pruning redundant task-specific parameters. During fine-tuning, many models' parameters are adjusted. However, most of these adjustments are minor and don't significantly contribute to the model's performance on the task. 31 adjustments that don't contribute to the model's performance are considered redundant. In the paper Ties Merging, Resolving Interference When Merging Models, Yadav et al., 2023, showed that you can reset a large portion of task vector parameters with minimal performance degradation, as shown in figure 7:17. Resetting means changing the fine-tuned parameter to its original value in the base model, effectively setting the corresponding task vector parameter to 0. Recall that the task vector can be obtained by subtracting the base model from the fine-tuned model. Figure 7:17. In Yadav et al. S experiments, keeping the top 20% of the task vector parameters gives comparable performance to keeping 100% of the parameters. Fine-tuning techniques, 353. 32 ties is abbreviated from trim, elect sign, and merge, while DARE is from drop and rescale. I know, these abbreviations pain me too. 33 When task vectors are pruned, they become more sparse, but the fine-tuned model doesn't. Pruning, in this case, isn't to reduce the memory footprint or inference latency, but to improve performance. These redundant parameters, while not harmful to one model, might be harmful to the merged model. Merging techniques such as ties, Yadav et al., 2023, and Dare, Yu et al., 2023, first prune the redundant parameters from task vectors before merge them. 32 Both papers showed that this practice can significantly improve the quality of the final merged models. The more models there are to merge, the more important pruning is because there are more opportunities for redundant parameters in one task to interfere with other tasks. 33 Layer stacking. In this approach, you take different layers from one or more models and stack them on top of each other. For example, you might take the first layer from Model 1 and the second layer from Model 2. This approach is also called pass-through or Franken merging. It can create models with unique architectures and numbers of parameters. Unlike the merging by summing approach, the merged models resulting from layer stacking typically require further fine-tuning to achieve good performance. One early success of Franken merging is Goliath 120B, Alpendale, 2023, which was merged from two fine-tuned Llama 2-70B models, Swin and Uriali. It took 72 out of 80 layers from each model and merged them together. Layer stacking can be used to train mixture of experts, MO, models, as introduced in sparse upcycling, training mixture of experts from dense checkpoints, Komatsuzaki et al., 2022. Rather than training an MOE from scratch, you take a pre-trained model and make multiple copies of certain layers or modules. A router is then added to send each input to the most suitable copy. You then further train the merged model along with the router to refine their performance. Figure 7.18 illustrates this process. Komatsuzaki et al. Showed that layer stacking can produce models that outperform MO models trained from scratch. Using this approach, Together AI mixed 6 weaker open-source models together to create mixture of agents, which achieved comparable performance to OpenAI's GPT-4o in some benchmarks, Wang et al., 2024. 354, Chapter 7, Fine-Tuning. Figure 7.18. You can create an MO model from a pre-trained model. Image adapted from Komatsuzaki et al. 2022. An interesting use case of layer stacking is model upscaling. Model upscaling is the study of how to create larger models using fewer resources. Sometimes, you might want a bigger model than what you already have, presumably because bigger models give better performance. For example, your team might have originally trained a model to fit on your 40 GB GPU. However, you obtained a new machine with 80 GB, which allows you to serve a bigger model. Instead of training a new model from scratch, you can use layer stacking to create a larger model from the existing model. One approach to layer upscaling is depthwise scaling. Kim et al. 2023 used this technique to create Solar 10. 7B from one 7B parameter model with 32 layers. The procedure works as follows: 1. Make a copy of the original pre-trained model. 2. Merge these two copies by summing certain layers, summing 2 layers and turning them into 1 layer, and stacking the rest. The layers to be summed are carefully selected to match the target model size. For Solar 10. 7B, 16 layers are summed, leaving the final model with 32 times 2 minus 16 is equal to 48 layers. 3. Further train this upscaled model toward the target performance. Figure 7.19 illustrates this process. Fine-tuning techniques, 355. Figure 7.19. Use depthwise scaling to create a 48-layer model from a 32-layer model. The image is licensed under CC by 4.0 and was slightly modified for readability. Concatenation: instead of adding the parameters of the constituent models together in different manners, you can also concatenate them. The merged component's number of parameters will be the sum of the number of parameters from all constituent components. If you merge two LoRa adapters of ranks R1 and R2, the merged adapter's rank will be R1 plus R2, as shown in Figure 7.20. Figure 7.20. If you merge two LoRa adapters using concatenation, the rank of the merged adapter will be the sum of both adapters' ranks. 356, Chapter 7, Fine-tuning. 34. I debated for a long time whether to include the concatenation technique in this book, and decided to include it for completeness. 35. In college, I made the painful mistake of letting my model train overnight, only to have it crash after 8 hours because I tried to save the checkpoint in a non-existent folder. All that progress was lost. Concatenation isn't recommended because it doesn't reduce the memory footprint compared to serving different models separately. Concatenation might give better performance, but the incremental performance might not be worth the number of extra parameters. 34. Fine-tuning tactics. This chapter has discussed multiple fine-tuning approaches, what problems they solve, and how they work. In this last section, I'll focus on more practical fine-tuning tactics. Fine-tuning frameworks and base models. While many things around fine-tuning, deciding whether to fine-tune, acquiring data, and maintaining fine-tuned models, are hard, the actual process of fine-tuning is more straightforward. There are 3 things you need to choose: a base model, a fine-tuning method, and a framework for fine-tuning. Base models. Chapter 4 already covered the criteria for model selection that can be applied to both prompt-based methods and fine-tuning. Some of the criteria discussed include model size, licenses, and benchmark performance. At the beginning of an AI project, when you're still exploring the feasibility of your task, it's useful to start with the most powerful model you can afford. If this model struggles to produce good results, weaker models are likely to perform even worse. If the strongest model meets your needs, you can then explore weaker models, using the initial model as a benchmark for comparison. For fine-tuning, the starting models vary for different projects. OpenAI's Fine-Tuning Best Practices document gives examples of 2 development paths, the progression path and the distillation path. The progression path looks like this: 1. Test your fine-tuning code using the cheapest and fastest model to make sure the code works as expected. 35. 2. Test your data by fine-tuning a middling model. If the training loss doesn't go down with more data, something might be wrong. Fine-tuning techniques. 357. Run a few more experiments with the best model to see how far you can push performance. 4. Once you have good results, do a training run with all models to map out the price/performance frontier and select the model that makes the most sense for your use case. The distillation path might look as follows. 1. Start with a small dataset and the strongest model you can afford. Train the best possible model with this small dataset. Because the base model is already strong, it requires less data to achieve good performance. 2. Use this fine-tuned model to generate more training data. 3. Use this new dataset to train a cheaper model. Because fine-tuning usually comes after experiments with prompt engineering, by the time you start to fine-tune, ideally, you should have a pretty good understanding of different models' behaviors. You should plan your fine-tuning development path based on this understanding. Fine-tuning methods. Recall that adapter techniques like LoRa are cost-effective but typically don't deliver the same level of performance as full fine-tuning. If you're just starting with fine-tuning, try something like LoRa, and attempt full fine-tuning later. The fine-tuning methods to use also depend on your data volume. Depending on the base model and the task, full fine-tuning typically requires at least thousands of exam-pleas and often many more. PEFT methods, however, can show good performance with a much smaller dataset. If you have a small dataset, such as a few hundred exam-pleas, full fine-tuning might not outperform LoRa. Take into account how many fine-tuned models you need and how you want to serve them when deciding on a fine-tuning method. Adapter-based methods like LoRa allow you to more efficiently serve multiple models that share the same base model. With LoRa, you only need to serve a single full model, whereas full fine-tuning requires serving multiple full models. Fine-tuning frameworks. The easiest way to fine-tune is to use a fine-tuning API where you can upload data, select a base model, and get back a fine-tuned model. Like model inference APIs, fine-tuning APIs can be provided by model providers, cloud service providers, and third-party providers. A limitation of this approach is that you're limited to the base models that the API supports. Another limitation is that the API might not expose all the knobs you can use for optimal fine-tuning performance. Fine-tuning APIs are suitable for those who want something quick and easy, but they might be frustrating for those who want more customization. 358, Chapter 7, Fine-tuning. You can also fine-tune using one of many great fine-tuning frameworks available, such as LLama Factory, Unslove, PEFT, Axolotl, and LitGPT. They support a wide range of fine-tuning methods, especially adapter-based techniques. If you want to do full fine-tuning, many base models provide their open-source training code on GitHub that you can clone and run with your own data. Llama Police has a more comprehensive and up-to-date list of fine-tuning frameworks and model repositories. Doing your own fine-tuning gives you more flexibility, but you'll have to provision the necessary compute. If you do only adapter-based techniques, a mid-tier GPU might suffice for most models. If you need more compute, you can choose a framework that integrates seamlessly with your cloud provider. To fine-tune a model using more than one machine, you'll need a framework that helps you do distributed training, such as DeepSpeed, PyTorch Distributed, and Colossal AI. Fine-tuning hyperparameters depending on the base model and the fine-tuning method. There are many hyperparameters you can tune to improve fine-tuning efficiency. For specific hyperparameters for your use case, check out the documentation of the base model or the fine-tuning framework you use. Here, I'll cover a few important hyperparameters that frequently appear. Learning rate. The learning rate determines how fast the model's parameters should change with each learning step. If you think of learning as finding a path toward a goal, the learning rate is the step size. If the step size is too small, it might take too long to get to the goal. If the step size is too big, you might overstep the goal, and, hence, the model might never converge. A universal optimal learning rate doesn't exist. You'll have to experiment with different learning rates, typically between the range of 1 times 10 to the power of -7 to 1 times 10 to the power of -3, to see which one works best. A common practice is to take the learning rate at the end of the pre-training phase and multiply it with a constant between 0, 1 and 1. The loss curve can give you hints about the learning rate. If the loss curve fluctuates a lot, it's likely that the learning rate is too big. If the loss curve is stable but takes a long time to decrease, the learning is likely too small. Increase the learning rate as high as the loss curve remains stable. You can vary learning rates during the training process. You can use larger learning rates in the beginning and smaller learning rates near the end. Algorithms that determine how learning rates should change throughout the training process are called learning rate schedules. Fine-tuning techniques. 359. 36. While it's commonly acknowledged that small batch sizes lead to unstable training, I wasn't able to find good explanations for why that's the case. If you have references about this, please feel free to send them my way. 37. I tried to find the first paper where gradient accumulation was introduced but couldn't. Its use in Deep Learn ing was mentioned as early as 2016 in AKO, Decentralized Deep Learning with Partial Gradient Exchange, Wacharapachat et al., Proceedings of the 7th ACM Symposium on Cloud Computing, 2016. The concept seems to come from distributed training, where gradients computed on different machines need to be accumulated and used to update the model's weights. Batch size. The batch size determines how many examples a model learns from in each step to update its weights. A batch size that is too small, such as fewer than 8, can lead to unstable training. 36. A larger batch size helps aggregate the signals from different examples, resulting in more stable and reliable updates. In general, the larger the batch size, the faster the model can go through training examples. However, the larger the batch size, the more memory is needed to run your model. Thus, batch size is limited by the hardware you use. This is where you see the cost versus efficiency trade-off. More expensive compute allows faster fine-tuning. As of this writing, compute is still a bottleneck for fine-tuning. Often, models are so large, and memory is so constrained, that only small batch sizes can be used. This can lead to unstable model weight updates. To address this, instead of updating the model weights after each batch, you can accumulate gradients across several batches and update the model weights once enough reliable gradients are accumulated. This technique is called gradient accumulation. 37. When compute cost isn't the most important factor, you can experiment with different batch sizes to see which gives the best model performance. Number of epochs. An epoch is a pass over the training data. The number of epochs determines how many times each training example is trained on. Small datasets may need more epochs than large datasets. For a dataset with millions of examples, 1 to 2 epochs might be sufficient. A dataset with thousands of examples might still see performance improvement after 4 to 10 epochs. The difference between the training loss and the validation loss can give you hints about epochs. If both the training loss and the validation loss still steadily decrease, the model can benefit from more epochs and more data. If the training loss still decreases but the validation loss increases, the model is overfitting to the training data, and you might try lowering the number of epochs. 360, Chapter 7, Fine-Tuning. Prompt loss weight. For instruction fine-tuning, each example consists of a prompt and a response, both of which can contribute to the model's loss during training. During inference, however, prompts are usually provided by users, and the model only needs to generate responses. Therefore, response tokens should contribute more to the model's loss during training than prompt tokens. The prompt model weight determines how much prompts should contribute to this loss compared to responses. If this weight is 100%, prompts contribute to the loss as much as responses, meaning that the model learns equally from both. If this weight is 0%, the model learns only from responses. Typically, this weight is set to 10% by default, meaning that the model should learn some from prompts but mostly from responses. Summary. Outside of the evaluation chapters, fine-tuning has been the most challenging chapter to write. It touched on a wide range of concepts, both old, transfer learning, and new, PEFT, fundamental, low-rank factorization, and experimental, model merging, mathematical, memory calculation, and tactical, hyperparameter tuning. Arranging all these different aspects into a coherent structure while keeping them accessible was difficult. The process of fine-tuning itself isn't hard. Many fine-tuning frameworks handle the training process for you. These frameworks can even suggest common fine-tuning methods with sensible default hyperparameters. However, the context surrounding fine-tuning is complex. It starts with whether you should even fine-tune a model. This chapter started with the reasons for fine-tuning and the reasons for not fine-tuning. It also discussed one question that I have been asked many times: when to fine-tune and when to do RAG. In its early days, fine-tuning was similar to pre-training, both involved updating the model's entire weights. However, as models increased in size, full fine-tuning became impractical for most practitioners. The more parameters to update during fine-tuning, the more memory fine-tuning needs. Most practitioners don't have access to sufficient resources, hardware, time, and data to do full fine-tuning with foundation models. Many fine-tuning techniques have been developed with the same motivation, to achieve strong performance on a minimal memory footprint. For example, PEFT reduces fine-tuning's memory requirements by reducing the number of trainable parameters. Quantized training, on the other hand, mitigates this memory bottleneck by reducing the number of bits needed to represent each value. After giving an overview of PEFT, the chapter zoomed into LoRa, why and how it works. LoRa has many properties that make it popular among practitioners. On top summary 361. Of being parameter efficient and data efficient, it's also modular, making it much easier to serve and combine multiple LoRa models. The idea of combining fine-tuned models brought the chapter to model merging. Its goal is to combine multiple models into one model that works better than these models separately. This chapter discussed the many use cases of model merging, from on-device deployment to model upscaling, and general approaches to model merging. A comment I often hear from practitioners is that fine-tuning is easy, but getting data for fine-tuning is hard. Obtaining high-quality annotated data, especially instruction data, is challenging. The next chapter will dive into these challenges. 362, Chapter 7, Fine-Tuning. 1. The increasing importance of data is reflected in how data effort changed from GPT-3 to GPT-4. In the contribution list for GPT-3, OpenAI, 2020, only 2 people were credited with data collecting, filtering, and deduplicating, and conducting overlap analysis on the training data. This dramatically changed 3 years later. For GPT-4, OpenAI, 2023, 80 people were credited for being involved in different data processes. This list doesn't yet include data annotators that OpenAI contracted through data providers. For something that sounds as simple as a ChatML format, 11 people were involved, and many of them are senior researchers. Back in their 2016 AMA, Ask Me Anything thread, Wojciech Zaremba, one of OpenAI's co-founders, said that they intended to conduct most of their research using publicly available datasets. Chapter 8 Dataset Engineering. The quality of a model depends on the quality of its training data. The best ML team in the world with infinite compute can't help you fine-tune a good model if you don't have data. The goal of dataset engineering is to create a dataset that allows you to train the best model, ideally within your allocated budget. As fewer companies can afford to develop models from scratch, more are turning to data to differentiate their AI performance. As models demand more data, data handling becomes more challenging and demands more investments in talent and infrastructure. Data operations have evolved from side tasks that people handle when they have time to dedicated roles. Many AI companies now employ data labelers, dataset creators, and data quality engineers, either integrated into or working alongside their core engineering teams. If the model landscape is confusing enough with numerous offerings, the data landscape is even more complex, with an ever-growing array of datasets and techniques being introduced. This chapter gives you an overview of the data landscape and considerations to take into account when building your own dataset. It begins with data curation, addressing questions like what data do you need? How much? What does it mean for data to be of high quality? It then discusses techniques for data synthesis and processing. Data curation, generation, and processing don't follow a linear path. You'll likely have to go back and forth between different steps. For the same model, different training phases aim to teach the model different capabilities, and, therefore, require datasets with different attributes. For example, data quantity for pre-training is often measured in the number of tokens, whereas data quantity for supervised fine-tuning is often measured in the number of examples. However, at a high level, their curation processes follow the same principle. This chapter focuses on post-training data because that's more relevant to application developers. However, I'll also include lessons from pre-training data when these lessons are insightful for post-training. There are best practices you can follow and tools that you can use to automate parts of the process. However, data will mostly just be toil, tears, and sweat. A data-centric view of AI. The increasing focus on data during AI development has given rise to data-centric AI, as opposed to model-centric AI. Model-centric AI tries to improve AI performance by enhancing the models themselves. This involves designing new architectures, increasing the sizes of the models, or developing new training techniques. Data-centric AI tries to improve AI performance by enhancing the data. This involves developing new data processing techniques and creating high-quality datasets that allow better models to be trained with fewer resources. In the early days of deep learning, many AI benchmarks were model-centric. Given a dataset like ImageNet, people try to train the best possible model using the same dataset. In recent years, more benchmarks have become data-centric. Given the same model, people try to develop a dataset that gives this model the best performance. In 2021, Andrew Ng launched a data-centric AI competition where participants needed to improve upon the same base dataset by applying techniques such as fixing incorrect labels, adding edge case examples, augmenting data, etc. In 2023, DataComp, Gadre et al., 2023, hosted a competition whose goal was to create the best dataset for training a CLIP model, Radford et al., 2021. A standardized script trains a CLIP model on each submitted dataset. The quality of a dataset is evaluated based on its resulting model's performance on 38 downstream tasks. In 2024, they hosted a similar competition to evaluate datasets for language models with scales from 412M to 7B parameters, Lee et al., 2024. Other similar data-centric benchmarks include DataPerf, ML Commons, 2023, and Bench, Ayuboglu and Carlos, 2022. 364, Chapter 8, Dataset Engineering. 2. If you use a lot of data, ensuring data compliance alone can be a full-time job. The model-centric and data-centric division helps guide research. In reality, however, meaningful technological progress often requires investment in both model and data improvements. Data curation. While not all issues with AI models can be solved with data, data is often a key part of the solution. The right data can make the model more capable, safer, and able to handle longer contexts. Conversely, poor data can cause the model to increase biases and hallucinations. Mistakes in data can harm the model and waste resources. Data curation is a science that requires understanding how the model learns and what resources are available to help it learn. Dataset builders should work closely with application and model developers. In a small team, they might be the same person. The person responsible for training a model is also responsible for acquiring the data for it. However, organizations with high data demands often employ specialized roles. 2. What data you need depends on your task and what you want to teach the model. For self-supervised fine-tuning, you need sequences of data. For instruction fine-tuning, you need data in the instruction, response format. For preference fine-tuning, you need data in the instruction, winning response, losing response format. To train a reward model, you can use the same data format as preference fine-tuning or use data with annotated scores for each of your examples in the instruction, response, score format. Training data should exhibit the behaviors you want your model to learn. Acquiring high-quality data annotations is always challenging. But it's even more challenging if you want to teach models complex behaviors such as chain of thought, COT, reason ing, and tool use. Let's go over these 2 examples to understand why. Chain of thought is discussed in Chapter 5. COT prompting nudges the model to work through a problem step by step before producing the final answer. To teach a model to generate step-by-step responses, its training data should include COT responses. Scaling instruction fine-tuned language models, Chun et al., 2024, shows that incorporating step-by-step responses in the fine-tuning data greatly enhances the performance of models of various sizes on COT tasks, with accuracy nearly doubling for certain tasks. Data curation, 365. Generating multi-step responses can be tedious and time-consuming. Explain ing. How to solve a math problem step by step is much more challenging than simply giving the final answer. To illustrate this, here are 2 examples, one with only the final answer and one with COT. Both are from Chun et al. 2024 instruction. Please answer the following question. What is the Boyle ing point of nitrogen? Response, without COT, -320. For F-COT instruction, answer the following question by reasoning step by step. The cafeteria had 23 apples. If they used 20 for lunch and bought 6 more, how many apples do they have? Response, with COT, the cafeteria had 23 apples originally. They used 20 to make lunch. So they had 23 minus 20 is equal to 3. They bought 6 more apples, so they have 3 plus 6 is equal to 9. As a result, COT datasets are less common compared to other instruction datasets. Tool use. Given the vast amount of knowledge a model acquires during pre-training, many models might intuitively know how to use certain tools. However, a model's tool use ability can be improved by showing it tool use examples. It's common to use domain experts to create tool use data, where each prompt is a task that requires tool use, and its response is the actions needed to perform that task. For example, if you want data to fine-tune a model to act as a personal assistant, you might want to ask professional personal assistants what types of tasks they usually perform, how they perform them, and what tools they need. If you ask human experts to explain how they do things, they might miss certain steps, either because of faulty memory or because they might think these steps aren't important. It's often necessary to observe how humans perform these tasks to ensure accuracy. However, what's efficient for humans might not be efficient for AI, and vice versa. As a result, human annotations might not be ideal for AI agents. For example, a human might prefer a web interface, whereas it's easier for a model to use an API. To search for something, a human might first open a browser, copy and paste that query into the search bar, and click on each result. Meanwhile, a model can just send a request to the search API with the query and process all the results at once.